Hi guys, welcome for yet another MDE paper of the week. This time I've chosen a 2010 paper, a UML profile for feature diagrams, initiating a model-driven engineering approach for software product lines. This is a Possompès, Donny, Houchard, Rey, Tibermacin and Vasquez paper. It's very interesting and very apropos, I guess, of what we're doing in Dogen. We are almost ticking all the boxes here. We're using feature diagrams, we're using feature models, I guess, MDE, and we're trying to do software product lines, and we are trying to integrate with a single view of modeling. So I mean, they talk about UML. UML for us is just a vehicle for transporting data, but the general idea remains that we would like to have where we have our structural modeling, we would also like to have our variability modeling. So if you abstract yourself slightly from the fixed aspects of this title, it is actually quite relevant to what we're trying to do. So let's have a quick look at the abstracts. This paper proposes an instrumented approach to integrate feature diagrams with UML models via UML profiles and rational software architecture plugin, and a rational software architecture plugin. The concrete contribution is the specification of a new UML profile based upon a meta-model synthesizing existing feature diagram semantics and a rational software architect implementation. Our RSA implementation makes possible to link feature diagrams with UML model artifacts. Indeed, it allows traceability between feature models and other different kinds of models, requirements, class diagrams, sequences, or activity diagrams. So many things here are not relevant for us, but a few are quite relevant. So this bit here is extremely relevant. Just have to be careful with our usual highlighting issues. We don't particularly care about the details of their implementation using rational. Again, this is also rather relevant. Of course, we need to press the right keys. Well, to be fair, might as well highlight the whole thing. Just start again. So if we delete these highlights and then just highlight all the way up to here, though we don't really care about rational aspects, but and then RSA implementation makes it possible to link feature diagrams with UML artifacts. Okay. Indeed, it allows traceability. Well, to be fair, I think yet again we find ourselves highlighting the entire abstract, possibly with a different color. Traceability. To be honest, I think perhaps the first bit is more important than the second bit, but both of the cases are quite important. The traceability is very important. We need to really work on the traceability. We still have quite a lot of things to do in traceability, but let's have a look at how this was achieved. So, introduction. Complex IT projects require efficient tools to support IT analysts, architects, and developers when they gather client requirements, domain expert advice, and implement software. This is the case in the context of the RIDER projects. Presumably this is their project. The RIDER project, research for IT as a driver of energy efficiency. It's led by a consortium of several companies and research laboratories including IBM and the LIRMM laboratory, interested in improving building efficiency by instrumenting it. Interesting. Whose purpose is to improve energy efficiency of buildings. We think that software product line approach is perfectly appropriate to manage the variations that can be found in our project, and moreover, feature diagrams will be great help at gathering specific domain vocabulary and concepts. Now, their purpose is a little bit different from ours, so let's just put a highlight here and perhaps a note. Purpose is so objective is more is life cycle. So the authors of the paper are targeting analysis and requirements. Really difficult spelling at this time of the day. Gathering as well as to film one on, as well as the more traditional development modeling. We have no such requirements. Okay, so in this paper we propose the creation of UML2 profile from a state-of-the-art feature meta model and the corresponding rational software architecture plugin. The instrumented approach enables integrating and federating feature diagrams with UML models and artifacts, requirements, class diagrams, sequences or activity diagrams, deployments diagrams. It is intended to be used as part of a general approach, for software product lines and for product generation. Again, just basically say, however, they do target SPL as we do. This paper is organized as follows. Section 2 presents the feature meta model. Section 3 describes how the profile has been derived from the meta model. Section 4 presents how the profile has been implemented in the modeling tool, validated against industrial concerns and feature diagrams excerpts from our project. And Section 5 sums up what is being presented and presents perspectives for further research. Okay, all very interesting. A feature meta model. This section describes the meta model synthesizing the different interest points that we previously identified after the state-of-the-art submitted POS. Oh. So, right, so what they've got here basically is a paper that describes the requirements for the design of the feature diagram. We're not too keen on that just yet, so let's just leave that for later. We chose to transform this meta model into a UML profile to facilitate the integration to ML models. This work is based upon ASI 06, which describes the domain ontology for feature models, and on the main reference, actually, I think we probably should have a look at ASI 06. This might be of interest. Let's just make sure we capture this in our bibliography notes. Put it here. This could be of interest. Actually, I wonder if when we click on a link, if oh, it's actually trying to give me a note. So let's say I click on another link, and then I wonder if I could just do a pop mark. Okay. No, unfortunately it doesn't look like clicking on links on PDF tools pushes the mark, which would be quite nice because then it would take you back to the page where you were. Oh well. We chose to transform this meta model into a UML profile to facilitate the integration into ML models. This work is based upon ASI 06, which describes a domain ontology for feature models and on the main references on feature models. So quite a few papers here. We complete this paper in the way that we produce a meta model that we are using in a very rich industrial project. Our profile implementation is done using Rational Software Architect and developed using a tooling plugin based upon our UML profile. Okay, a lot of motivation here. As depicted in Figure 1a, a product line contains features. A product belongs to one product line and is composed of features. Features associated to a product must check some constraints like mutual exclusion or required relations. Mutual exclusion and required relations are modeled by the conflicts and required relationships. The recommends relationship advises the user to choose another feature that could be pertinent. Okay, let's have a quick look at this then. So we have a notion of a product line, and a feature. Product line is made up of products, Product lines contain features, products also contain features. Features then can have these recommended features and the conflicting features. Features have properties, and there we are, feature property, and principal modification, not quite sure what this means. Variability kinds, and there's kinds of variability, whether it's fixed variable, family variable, or user defined. Okay, let's have a look at what that means. Feature properties in figure 1b describe either a feature parameter. Well, to be honest, I think I would like to highlight pretty much everything we got up to here, because we need to review our variability model against some of these feature models, make sure we capture everything. So it is worthwhile highlighting these bits here. And now let's have a look at the rest. Feature properties in figure 1b describe either a feature parameter, e.g. the bandwidth capacity of a network, or a property chosen by the user, e.g. the frequency of automatic backups of a word processing software. The variability kind can be fixed when the feature property value is fixed throughout all products of the product line, not particularly useful, I guess. Variable when the feature property can change within the product line depending on other feature properties. Family variable when the feature property could vary from product to product according to the selected features. And user defined when the feature property can be chosen freely in a given product. So in our particular case, we find this is actually a useful way of classifying things, although it doesn't really fit us directly, because if we look at our variability model, it is possible to define features. So let's take as an example some of the features we defined in the logical model. So as you can see here, there's a whole lot of feature bundles here. Again, this is still pre-terminology review, so names like feature bundle is still in use. And here you can create features such as targets and so forth. And these features then contain parameters such as optionality and so forth. So we have some overlapping with what is defined in the paper. We probably should make sure we look at this. And we probably should try to capture the core of these entities here. Feature elements, feature model elements, presumably. Let's just put a few here. So product line contains features and products key elements of feature model. Now this is of course on that domain ontology, but nevertheless we'll just grab it. So product contains features and belongs to the product line, and features associated with the product may have constraints such as require relations and mutual exclusions. Mutual exclusion require relations modeled by conflict. Okay, that's fine, we don't care about that. And then feature properties. So features have feature properties. These describe feature parameters. Properties chosen by the user. Not very clear exactly what the difference in the two. Variability kinds. So variability kinds fixed, constant, not particularly useful as I say. Variable can be changed. in a product. Depending on other features. It's interesting. Family variable can change from product to product and user defined the user. We're not entirely sure how we're going to apply this variability kinds, but it's good to know this. They model it this way. Figure 2 presents hierarchy, relationships, and sub-feature groups. A feature and its sub-features are connected. Right, okay, so interestingly, they decided to call these sub-features. Okay, so feature can have sub-features. This is a better term than feature bundles. So we need to understand really what is meant by these features and sub-features. Features and sub-features are connected by the relationship group class that contains the cardinalities necessary to restrict the number of sub-features to choose. Right, so of course what they're going to do here with the sub-features is going to basically say that these things are sort of options you can choose within a given feature, which is not what we want. We use special groups like the OR group with cardinalities like 0 star, and the AND group with cardinalities like star star, and the SHORE group with cardinalities 0 1. A directed binary relationship links a parent feature and its sub-feature. It can be specialized either by enriched, implement, or detail classes. Yeah, so it's not really what we want, because otherwise we end up saying that every feature is kind of an AND group, because we want all the features. They're kind of really one of the problems we always find with feature modeling is that people tend to always group features into some kind of you define the feature, and then in the feature we got some kind of checkbox or combo box of choices in that feature, and these are what tends to be mapped as sub-features. But really much more useful than that would be to be able to just group a bunch of features together, because a lot of the times you basically try and say these guys here all belong together. Like if you look at our use cases, the vast majority of cases, all we want to say is something really simple. I have a bundle of features here related to ORM mapping, and we would like these features to all be treated as a unit for certain purposes, because when we read them out, when we process them in one go. We don't really want to say that if that's enabled, that's not enabled, or this disables that. Those really complex relationships are not actually that useful for our use cases. But that's what everyone seems to be focusing on, which is a bit of a shame. Of course, you could say that the AND group is probably sufficient to model this, but then it begs the question as to why go through all this complexity of ORs and SHOREs and all of that, when 99.9% of the time you don't actually use any of that machinery. So yet again, I think we should probably highlight this again. And maybe we should just say here something like sub-features. As with most papers on the subject of feature models, the grouping of features is done mainly to allow for relationships for complex, should I say, relationships between I don't think I pressed the right option there. Between the features in the group. Our main use case is quite trivial. We just need to group features as if... Oh, one thing we did forget is to start clocking. So, well, I guess we can figure out the time by looking how long we've been recording. We need just to group the features as if in a namespace, in a package, let's say. we could, of course, make use of relationship such as the ends group, but it's not clear why one would implement all of the complex logic around feature relationships if we only require the simplest use case. So there what you must understand, of course, is that because we have a very specific way in which we're using feature models, which is just purely for development level modeling, a lot of the richness of feature models is actually just overkill. If you were probably doing something really complicated like modeling requirements or something like that, presumably all these things come in handy. But for a developer that's just modeling a class with a few things here and there, the complex power of feature models is just not needed in a lot of the cases, really. At least that's how we view it. I'm not saying that's for all the cases, but specifically in our use case. Figure 3 layers. In figure 3, layers and feature sets are linked to the project stakeholders. The stakeholder, like as we said just a second ago, here we are for the more complex use cases. A stakeholder represents any kind of people, customers, domain experts, IT architects, etc., that can be led to choose features. Feature sets and layers are attached to a specific concern related to the project. A layer represents a view onto the software application. A feature set is a feature. Here we are. Feature set. A feature set is a feature which groups features from an arbitrary point of view. Okay, there we are. So, however, the authors put forward the notion of a feature set, which seems to be the ideal candidate for our feature bundles. Okay, that's good, because now at least we have a proper domain term. So a feature set is a feature which groups features from an arbitrary point of view, e.g. for a business domain. So feature sets group features from an arbitrary point of view. This is what we do when modeling features. It also represents features that must be implemented to fulfill a norm. Well, not sure about that second bit, but clearly this is what we've been looking for. And now we probably should go for a nice green here. Right, so let's have a quick look at figure 2 and 3. So here you can see the complex relationship between features. So, well, it's not to say we're never going to need this. At some point, perhaps we will need this, and specifically when we have cases where enablement is actually the most complex feature that we got. There's many cases where you want to say if this is enabled, then that should be disabled. So in those cases, clearly you're talking about this kind of complicated logic. This is the only case we found up so far that's actually really useful. So we probably will make a special case of it, and then we'll try to model as much as possible as a feature, but perhaps not with the full power of this. But more interestingly is the stakeholder concern, layers, and feature set. So really what we care about here is feature set, concerns, and the features. So that is actually quite a useful thing. Figure 4 depicts constraints on feature sets. A feature set can be either mutex, when only one feature can be selected in the feature set, none, where there is no constraint between the features composing the feature set, which is our case, and all, when all features or none of them can be selected. A constraint relation class is a relation between two feature sets. Hence, one feature set can require another one, two feature sets can mutually require each other, or be mutually exclusive. Okay, I feel a little bad because I think we're highlighting too much in this paper, because it seems like we're highlighting literally everything, but let's keep an eye on that. I mean, I slightly simplified things a little bit. I mean, so let's just think about it for a second. We do have things like ORM features, right? And then the idea here is the ORM feature is triggered when you annotate certain classes, right? So let's take an example, the relational model. So if you go up to the relational model, now this is a use of the relational model. You can see here we are starting to annotate certain things as ORM. So for example, we annotated this object here as an ORM value. Once you annotated this as an ORM value, what then happens is that you then trigger the ORM features. In other words, these features are only enabled because you've chosen a certain stereotype. Now, up to now, we didn't really generalize this. We didn't really make it so that the stereotype itself is a feature or something like that, and then there's a dependency between features. There's only one very specific use cases for this, and generalization seems a bit expensive. So we haven't actually done that. But you can see where they're coming from, and you can see if you were to do that, that generalization could be useful. So probably should say something about that. Feature sets enable complex relationships between features and feature sets themselves. We could probably use some of this. For example, if ORM stereotypes were features, we could determine which ORM features are enabled or disabled on the back of it. However, this would require a lot of a generalization of lots of the handling that has been hard-coded thus far, and it's not obvious what advantages would be gained by this generalization. Okay, this should give us a bit of an idea what's going on here. Right, now let's get into the transformation method. Interestingly enough, we seem to just have a section 2.2 transformation method, but not a lot on it. This is probably a preprint, as always. We always go for preprints. Not a lot talking about transformation method, probably just a bug on the preprint. 3. Profile model. Okay, so now let's see how they mapped this over to UML. These are the constraint relations they're talking about. I think we should just leave it for now. Profile model. So the meta model describes the syntax of the elements used in a feature model. The profile reuses the concepts described in the meta model and integrates them in UML thanks to profile semantics. Creating UML profile consists in creating stereotypes that extend UML meta classes. Stereotypes are meant to add or subtract semantics from the meta classes they extend. So this is just basically generic UML. Hence, the first step is to create a profile from a meta model is to identify which meta classes should be transformed into stereotypes and which meta classes should be extended. Okay, this is, it's all very standard, but let's just highlight it for this is detailed in the next section. However, the profile could be implemented in very different ways by choosing to extend different meta classes. In our approach, we choose UML meta classes that add the closest semantic to our concepts. Right, this is probably a crucial thing. Of course, like everybody else, we will also have to extend some kind of UML. We'll have to define a profile. So we'll have to apply similar rationale. Okay, it seems like we highlighted the wrong thing. Still haven't quite got to grips with the whole highlighting on PDF tools, to be fair. Seem to sometimes work, sometimes not. Meta classes, extensions and attributes. So contrary to CLA 01, and I think I know what CLA 01 is going to be. Klaus. Interesting, this is German. Right, I'm pretty sure I have this paper Klaus, but in English. In fact, I'm quite certain. Let's have a quick look here. Check that this paper is the same one as we read in English. Forgot to use good old Emacs keys for copying and pasting. And to a good measure, let's highlight that as well. So Klaus, the Klaus paper that we read in English, he basically used classes for the feature models, which is kind of what we did as well. These guys are going to suggest something different. Contrary to class CLA01, Klaus, we chose to base our feature diagram on components. Right, as you can see here, this is a very big deviation. A component is the UML concept, which is the closest to what we want to express because it is an high-level view of a software element. Right, very interesting. This this first choice will influence the other UML metaclasses selection. For example, the port concept allows us to easily group associations to sub-features. This will be impossible if the feature stereotype was extending the classifier UML metaclass. Some associations of the meta model, well, actually, I disagree with this. So let's just highlight all of this. So what they're saying here is this. They're basically saying that they can't group associations to sub-features. This would be impossible, as the words they used, if the features stereotype was extended the classifier UML. Well, actually, classes have attributes, and attributes could represent features, which is exactly what we did. So some associations in the meta model have been implemented as stereotypes. So components. So let's just call this UML component as a feature. Authors use components to model features because ports allow expressing groups of associations of sub-features. Since we do not have a need for complex groups, the simple grouping that attributes enable us to do is sufficient. So this is a good way of explaining why we went for the approach we did. Feature stereotype, though, now he's going to describe what they've done. Feature stereotype extends the metaclass component. Stakeholder extends the actor metaclass because they have very close semantics. Concern extends the class metaclass because we will need class attributes to list layers and feature set references. Model relationship extends the dependency of a feature to any kind of UML artifact. Okay, let's have a quick look what we mean by model relationship actually. Let's put here investigate what a model relationship is. Presumably it's the base class for aggregations and so on. We shouldn't really call it base type, is the meta type. It's very easy to start breaking the M0, M1, M2 layers. Layer extends the package meta class to each grouping features into a single place. Product line extends package to centralize all software product lines artifacts in a single place. Okay, I quite like that actually. Sorry, with the noise downstairs. Product line extends package to centralize the software product focus in single place. Product extends component because it represents the features which are considered as a kind of components. So it's interesting. So they decided to use component for product. Let's just have a quick look at what we look like when we look at a component. So if I just create a component here, so this is what they use for a product. Can have a stereotype, interestingly enough. Okay, it's interesting. And these are the ports that were mentioned there before. Of course, dia is a very limited diagram, so you can't really extend things like ports and so on, but okay, that's interesting. So product extends component because it represents a set of features which are considered as a kind of components. Well, we will need to model products, so let's keep that in mind. Feature property stereotype. Stereotype extends port meta class to allows representing them as being artifacts directly attached to a feature. This can be linked to other ports or components. The modification of a feature property can be modeled by textual OCL constraints based upon the relationship between two feature properties. Okay, relationship group extends the port meta class to represent as belonging to the parent feature. Can be linked to only to other features with directed bind relationships. Okay, modification extends the usage meta class, and then the direct bind relationship extends the association meta class. Used to link ports to components. The binding predicate extends the port meta class in order to represent the kind of interfeature set constraint. The constraint relation extends the association meta class because it links two feature sets. It can be navigable or not. Okay, this is also something we may find useful in the future. So the resulting profile then. The constraint relation stereotype figure 6a corresponds to the meta model association required feature and conflicting feature. It is specialized into respectively the stereotypes mutual require and exclusion. It is not necessary to link their stereotypes to the feature stereotype because the association and component UML meta classes are already connected. The binding predicate single bond. Okay, we're going to get into a lot of details of their machinery. Single bond, multiple bond, all bond stereotypes, and figures 6b and 6c extend directly the corresponding meta classes. There is no need to link the binding predicate stereotype to the feature set stereotype because they respectively extend the port and component UML meta classes. They are already linked into the UML meta model. The feature set stereotype and its specializations are directly derived from corresponding meta classes. So let's highlight that. Now then, let's have a look. So we have a component, product line, and feature all derived from component. Stereotype. Feature set derives from feature. Class is used only for concerns. And stakeholder is inherited from actor. And then we have the binding predicate, which comes from ports, and then so this is all the stuff that comes out of ports. Okay, so the key thing really is once you've chosen components, then everything else kind of comes from there. It's a very important decision. And then we talk about the different relationships we got. Now the feature set stereotype is the more interesting one. So the feature set is here. Well, to be honest, not a lot of news here. It's just basically talking about the same thing, just bringing us back to the relationships, the model relationship. So the required feature and recommended feature aggregations have been modeled the same way that in the meta model because it is more convenient to have attributes in the feature stereotype. Figure 2, the list all the required and recommended features. Okay, we could also model these concepts with stereotypes extending associating UML, meta class rather than aggregation attributes. The stakeholder concerned layer feature set, product and product line stereotypes are derived from corresponding meta classes. However, interesting, derived from the corresponding meta classes. Okay. However, modeling element metaclass has been derived as modeling relationship stereotype extending the dependency UML metaclass. It represents the dependency between a feature and any UML element represented by the element UML metaclass. The feature property stereotype, figure 8, is now linked to the feature relationship because it extends the port UML metaclass, which is already linked to the component UML metaclass. The modification and changed feature property stereotypes extends the usage metaclass in order to show the impact of one feature property on another. The constraint attribute describes how the changed features must be impacted. The relationship between feature, figure 9, are directly derived from the meta model. Okay. The relationships between feature are directly derived from meta model. They are not linked to the feature stereotype because the port and association UML metaclass are already connected to the component UML metaclass. Fine. So feature property, change feature property, modification. So now we're trying to model the notion of changing features, and then we have the relationships. Okay. Implementation and validation. Common profile. Okay, right. So we probably don't need to look into a lot of detail into this, but it's going to be actually related to their implementation. Common profile implementation tools. The Eclipse modeling framework and the graphical modeling framework. So basically, they just used usual EMF stuff. The Eclipse modeling framework is a modeling framework integrated into the Eclipse platform, which can be used for building tools and applications based upon a structured data model. It integrates the core meta model, which is equivalent to the Open Management Group Essential MOF, basically EMOF. The base framework can be used to support any model. Indeed, it provides an implementation of the OMG UML2, which can be extended thanks to profiles, the standard UML extension mechanism. We needed a tool to create feature diagrams that could be integrated in software development lifecycle using UML. The graphical model framework enables us to develop graphical editor based on UMF that fits our needs. Okay, so this is the usual EMF sort of tooling. With it, you can literally create the whole sort of set of tools, including the editors and everything, and it gives you a really nice one-stop shop for everything. So Rational Software Architect profile. IBM Rational Software Architect is based on the Rational Modeling Platform, which provides UML modeler. Modeling editors use tools that are built by using various services offered by the platform. It also includes several helper components to work with UML models and diagrams. All models managed by Rational Modeling Platform are instances of EMF models. Most interesting. Hence, using Rational Software Architect allows us to simplify tasks like creating a specific plugin for integrating feature modeling capabilities into standard EMF-based UML models and diagrams. We chose to create a Rational Software Architect plugin instead of a standard Eclipse-based plugin. Indeed, it facilitates the tooling source code generation by deriving the code from models described in plugin architecture. Right, this is all implementation specific. We don't particularly care about any of this. Examples. Figure 10 describes the required features of a building management system. The user must choose one building XML schema to specify the standards describing its building and a scenario optimization set according to its building usage. So from here you can already see how their use cases are much more powerful, much more complex than ours really. In figure 11, the business layer contains the features that describe the energetic optimizations that could be done in a building. All features from the business layer are linked to one or several features from the execution model layer. It specifies which are the modeling standards able to provide the required data to each business feature. So now we enter the conclusions, and it's just around 43 minutes. We have presented how we implemented the feature profile in UML2. It's based upon a synthesis of existing work that we enhanced to fit the requirements of a project in which this research is applied. We created a Rational Software Architect plugin to be able, in a later time, to easily add functionalities required by our industrial project. We have modeled feature diagrams concerning building modeling standards and IT architecture components. We now need to automate the product generation process and enable the user interface for the plugin. Okay, and then we have our references. And okay, so in conclusion, quite an interesting paper. I still think we might end up having to go back to their design paper. So let's make sure we write a note on that. So this is really more focusing about the on the UML profile. We need to figure out how they gathered the requirements really, which is POS. So this paper is probably of interest because the gathering of the requirements is probably going to have some interesting points. Requirements for the feature model. We need to explain so how we've gathered the requirements for our feature model, and so it'll be quite good to make sure that we follow a similar process to what they've done. But the other interesting thing, of course, is that we have a terminology issue at the moment on our variability model, which is something that's one of the reasons why we're rereading some of these papers again. So what we've done when we created our feature model, and this is something we tidied up on the physical model now. In the physical model now we have very good separation between meta-model entities and model entities, and this is quite nice and quite clean. In the variability model we still haven't quite achieved that. So where we define a feature, we really are talking about the feature meta-model. And then we have instances of those features, which is the model. And so our feature model should really be composed of lots of instances of features and so on. But there are aspects here which are actually describing the feature meta model, and we have both of these issues kind of confused at the moment. And so these papers are going to help us to unpick the sort of the difficulties we have here in language. So this paper has helped us a little bit, especially in the feature set area, but we still need a few more papers in this. So all in all, very useful paper. Okay, thanks for watching.